Here's a typical question involving coils and magnetic fields. We've been asked to consider, is there a force on the right hand coil when we close the switch on the left hand coil? If you'd like to understand more what the answer is to this, then stay tuned to the end. Let's start with the coil on the left. Fairly obviously, before you close the switch, there is no current flowing. As you close the switch, however, the current is going to build up rapidly and then level off. Now this might only take a fraction of a second. Nevertheless, there's going to be a build up and a leveling. This in turn means, since there's a magnetic field associated with the current, that we're going to get a magnetic field in the coil which starts at nothing, builds up rapidly and then levels off to a constant. What we can say is that those lines of flux are going to flow either towards the second coil or away from the second coil. We don't know which, and in a way it doesn't matter. What we need to bear in mind is that it starts at nothing and then builds up to a constant value. The second coil initially starts off sitting in no magnetic field. When we close the switch on the first coil, the magnetic flux lines build up rapidly through the second coil, and then they reach a constant level and flatten out, just like we described. Faraday's law tells us that the EMF induced in the coil is proportional to the rate of change of flux. So at the end, when the magnetic flux flowing through the second coil is constant, there will be no EMF. However, as the magnetic flux lines in coil 2 build up rapidly, that point will give us an EMF. What we get in the second coil then could be summed up as a spike of EMF as the magnetic flux lines from coil 2 change, then going down to 0 again. Since we have a spike of EMF, we're also going to have a spike of current flowing in that coil. Lenz's law tells us that the induced EMF acts to oppose the change that created it. Well, there are lots of ways to think about this. What is the change that created it? You could say it's the current, in which case the current in the second coil will have to go the opposite way. But perhaps a clearer way to think about this is to think that actually it's not so much the current that induces the EMF as the increase in the magnetic flux density coming from the first coil. This means that the current in the second coil will be going in such a direction as to create field lines that flow in the opposite direction. That means if the field lines from coil 1 are left to right, the field lines from coil 2 will be right to left. Now we're in a position where we can work out what's happening with the force on the second coil. The simple way is to just realise that although we don't know which direction the magnetic flux from coil 1 is going, it's the opposite from coil 2. We therefore have two norths, or indeed two souths, facing each other, and so the second coil, assuming the first one is tied down, will shoot off to the right. So that we can see then that these two coils are going to experience an opposing force. Now this could be the basis for, say, some kind of gun type system where you could switch a button and the second coil attaches to a bullet and the bullet shoots off. In the lab you're only going to get relatively small forces, but you can actually make surprisingly big effects with magnetic fields if you wind up the number of turns and so on and so on. If you found that video interesting, try out this one.